Episode 73, Blanets and Squeezars. And welcome back for another edition of the Syzygy podcast. Joining me across the other side of the country as ever, Emily Brunston. Emily, how are you doing?
Hello. Yeah, I'm not too bad, getting through this lockdown 2.0.
Those of you who aren't in the great country of the United Kingdom, great bunch of countries of the United Kingdom, may not be aware that we are going through lockdown number two in a series of N, perhaps, who knows? But we're just coming to the end of that, and now we're figuring out all of the coronavirus tiers, T-I-E-R, T-E-I-R, how do you spell tier? I don't know. Trying to figure out exactly what conditions we're going to be living under in this country, and that's all loads of fun. So whatever you're dealing with coronavirus-wise in wherever you are, good luck with that as we battle on towards the end of what has been a very, very interesting year of 2020. You might have noticed we haven't been recording a hell of a lot over the last little while. Thank you to those of you who have been sort of checking in and going, Syzygy, are you still there? Are you still around? We are still around, and we are still intending to do this podcast regularly and frequently in the future. Just right now, we're just trying to pull everything together. Emily, in particular, you're looking forward to actually travelling, which staggers me. You're going to be heading off on an actual aeroplane to an actual other country, which is cool.
Well, I know, it sounds very glamorous now, doesn't it, in these strange times?
It sounds very much, it's kind of like we've just gone back in time. So in the future, people will get on planes and travel to other countries. No, that's not possible. But apparently it's true.
Yeah, no, I've been very fortunate to be able to get all the ducks in a row in terms of things like quarantine visas and actual flights, and I'm able to get back out to New Zealand for a short time over the next couple of months.
Which is staggering. So the next edition of this podcast will be live from the other side of the world, which will be very, very cool. But listen, let's get on with the show. Today we were going to talk about over the last while, we've had a few shows which have been about black holes. And you can't have too many shows about black holes, I reckon, because they're just so awesomely cool. You know, this strange part of the space-time continuum which has collapsed in on itself to a point where nothing can escape, and they're just freaky things. But today we're going to talk about things which go around black holes. Things which are using black holes as their gravitational center. Emily, what are we talking about today? We've got a couple of really nice terms that I'd never heard of before. What's the show about today?
Well, we're going to be looking at Blanets and Squeezars.
Blanets and Squeezars. All right, so we're going to have to delve into this one, take it apart one by one. Shall we start with Blanets then? Emily, what's a planet, and where is this new term in astronomy come from?
Well, I teased you just before and I said, well, maybe planets are planets which have really nice cozy blankets to take with them to bed each night.
You know what? Here in York today, it's cold and it's wet, and I could really use a planet right now. That'd be just nice. You could curl up with a nice cozy planet, and that'd be lovely. But that's not what we're talking about, is it? We're not talking about planets with nice blankies. We're talking about what?
Black hole planets.
Black hole planets. Now, sorry, this isn't a planet that is itself a black hole. That doesn't make any sense. So what are we talking about? Is it planets going around black holes?
Planets going around black holes, exactly.
I think I saw this film. Didn't I see this film? Isn't this basically the middle third of Interstellar? That's
Indeed.
The planet with the big waves on it, isn't it?
Well, yeah. Interstellar in some ways kind of preempted a little bit some of the things that we're going to be talking about, which is planets going around black holes, although as we'll talk about, they're maybe not quite as evocative and friendly as they are in the film. It was
an interesting part of the film. There are a number of things that I looked at in that particular part. And if you haven't seen Interstellar, I think it's been out long enough that we're not going to give away any big spoilers here, I don't think. But at one point in the film, the main protagonists go down onto a planet which is orbiting a black hole, which in itself is very cool for a bunch of reasons. One, because it's just a pretty funky idea. Two, because the whole concept of, but hang on, surely black holes, they're like just big vacuum cleaners, aren't they? Like big hoovers, don't they just suck up everything that comes nearby? No, they're just really, really massive things, which like every other really massive thing, like a star, they have a gravitational field around them and something can be in orbit around that. So that's fine. One of the really funky things about this part of the movie is that because the curvature of space-time is so strong around this black hole, they go down towards this planet and time does really, really weird stuff, doesn't it? So they sort of, whatever it is, a couple of days or something in the time frame of the protagonists becomes, a decade or something on the dude left behind on the spaceship, which is, I'm surprised he didn't just pull out a shotgun and start shooting people by the time they got back. One thing I wanted to know in that film, though, was they were down on the surface of that planet and it was like daylight. Like, where's the daylight coming from? You're in orbit around a black hole. Where's the daylight coming from?
Yeah, and they were sort of close enough that there were some shots of, that this is where the black hole is in relation to the planets. They weren't that far away from the black hole when they did those kind of shots, which was a little bit concerning. So, yeah. I mean, as we'll talk about, there is radiation coming from black holes, but it's maybe not the kind that you super really want to get
If you're looking for a habitable planet, avoid one with really, really big waves, spoiler, but also maybe avoid one around a really just nasty radiation source called a black hole. I don't know. I'm going out on a limb here. Anyway, that's enough about the film. Let's go from science fiction to science reality. Are you saying, Emily, that the film kind of preempted this and a bunch of astronomers watched the film and went, hey, there's a research grant in that. Should we go and look for some black hole planets? And by the way, let's coin a new term. Let's call them Blanets.
Well, it's a nice story, actually, in the sense that I can't comment on whether the astronomers in question here actually have seen the film and therefore wrote their funding grant based on it. But
I think someone should ask them if they haven't been asked. We should ask them.
So this is a team which was led by Wada from Japan. So various astronomers, and what they were looking at, they did a first piece of research which was published in November last year, which was kind of looking at, is there actually sort of a place that you could form planets around a black hole? Like, does this whole concept even work? And they were able to show that they had the safe zone, if you like, where you could form planets and they could orbit. And then following on from that, in July this year, which is why we sort of picked this up in the summer, and I think we promised this episode quite a while ago.
This one's been sitting there for a while on the whiteboard, the virtual whiteboard of Emily's virtual office, which is, we should do a show about that someday. Well, here we are.
Yeah, so in July they released the new preprint of kind of some more detailed calculations of how these planets could form. They solved some of the problems that they identified in the first paper. And so basically they were able to theorize using all the information that we know about the locations, the environment around black holes, and say, hey, look, actually you can form these planets here.
This is possible. Now, what's the problem here? Because, I mean, as I said a minute ago, in a sense, a black hole is just like any other massive object in the universe. Right? It's very concentrated. It's kind of weird. But when it comes to it, something nearby just simply sees it as a big, massive lump with a gravitational field as a result. And so it can orbit around it. But what's the problem here in the sense of, like, why was there any question about this? Surely if you've got a big lump of mass and a gravitational field thereof, then you can orbit around it. Why was there a question about that?
So there's no question really about the orbit. It's more about the formation. Can you actually form these things there in the first place?
Right.
So black holes have accretion disks in a very sort of similar broad way that stars, when they form, have accretion disks. So when a star collapses from a cloud of gas and dust, it forms this disk of material around it, and that disk, eventually in that disk, the planets are formed. So I guess the broad concept is the same. A black hole has this accretion disk of kind of all this material around it. Could that stuff kind of stick together and make planets?
Right.
Even though the environment is, pretty different.
It's pretty different, but in principle possible. Where does, like, when a star is forming, right? A star is forming out of a cloud of dust and junk in space. Whether that's the debris from previous stars or whatever. And it's forming out of the same material that the accretion disk ultimately becomes as well. When you've got a black hole, though, the black hole is like, that's the end of a star. That's the end of a star's life. So where's the accretion disk for a black hole come from?
Well, it's mostly come from all the stuff that's come a bit too close to the black hole, being torn apart and never been able to kind of form into stars and things from that point onwards. So, so these supermassive black holes, their origins are not particularly well understood, but there's probably things from galaxy mergers, things. So to make the supermassive black hole, you've got to kind of build up from smaller black holes, and it's likely that in the process of say small galaxies forming merging into bigger ones and then bigger galaxies merging together, that these just the leftover stuff, or the stuff that's been either never went into the stars from the interstellar medium from these galaxies, or stuff that's been ripped apart from these objects is just sort of lurking around in this disk.
Right. So we're talking about supermassive black holes, as opposed to your perhaps common or garden variety black hole left over from the death of a star. In this particular case, in this particular paper, in this particular study, we're talking about supermassive black holes, which are the ones that tend to be at the heart of galaxies. We think probably at the heart of all or most galaxies.
Yeah, pretty much. Yeah. And they come in a lot of different varieties, and we'll talk about the AGN varieties, which are the ones that are actively feeding black holes, which make active galactic nuclei.
Okay, so what you're saying then is supermassive black hole, they're going to tend to pretty badly disrupt their local environment, and so you end up with all sorts of things being torn apart by the ridiculously strong gravitational fields, and that's where your accretion disk comes from. And so this research which was released or updated back in July, in July, is about, in that accretion disk, can you maybe form planets in a sort of stable kind of way? Okay, and the answer to that is seemingly yes.
Yeah, all indicators point to yes.
Fantastic. So does that mean that we can now go and look for some? Have any been found? Is that a ridiculously impossible question?
I think we need to sort of look at what those planets might actually be, because they're not exactly what you might expect in terms of a copy of our solar system around a black hole.
Right. So what you're saying, we're not necessarily going and looking for another Earth going around one of these things. Okay, this is planets not as we know them?
Exactly. So the thing is with supermassive black holes, so these are black holes that are kind of 1 million times the mass of the sun, or maybe even more than that. So these are really, really sort of big, nasty objects. And when they become AGN, or they have an AGN property, when they're feeding, and we've talked about this a few times, where you have these big jets of material which come out. These jets are coming out perpendicular to the disks, if you like. So if you sort of imagine the geometry, then you've got the black hole, disk around the black hole, jets are firing off away from the disk.
As you say, the black hole is feeding, so there's material from the disk, the accretion disk around it, which is falling into the black hole, and that's a very energetic process. As you know, around the edge of the black hole, it's being torn apart. Some of the mass and energy goes into the black hole, and some of it gets spat out in the form of various kinds of radiation, and the massive magnetic fields and so on just sort of beam those off as these two beams up and down from the rotational axis. And so you've got these active galactic nuclei which are beaming out these crazy beams of radiation. Okay, so that's AGN.
Yep. So that's where the majority of the energy is being lost, but it's not the only way. They're radiating in all directions as well. So you get lots of radiation coming off and heating up the disk. So the very inner part of the disk is very, very hot. Which is why we can see it, for example, in the black hole images. This is all linked to the same physics, right?
Yes. Yeah. Which, I don't know about you, that feels like that must have been a century ago when those pictures came out. When was that?
Was that last year?
Last year? Was that 2019? Let's assume it was 2019. I have no idea. But yeah, amazing images of the supermassive black hole at the center, not the center of the Milky Way, was it? They were trying to do that.
Another galaxy.
Center of another galaxy. And what they actually took a picture of was the heated up accretion disk around the black hole.
Yeah, and part of it, and the photons that are kind of coming around it because of that. So you've got this accretion disk now. So the inner parts of that disk are going to be pretty hostile to anything happening, really. You've got pretty intense radiation coming from the black hole. It's pretty hot. And so when we talk about forming planets, what we need to form planets is a relatively calm environment, because you're thinking you've got tiny, tiny particles of dust that is forming this accretion disk. And And that sort of dust is it's micron sized. So it's cigarette smoke particles are kind of similar sized. And you've got to get these things, if you want to build a planet, you've got to get these things to stick together, right? If you make them too hot and if you give them too much energy and too much velocity, then these things are not going to stick together. They're just going to kind of bounce off each other, whiz around.
Right. So as you say, you need a fairly calm environment, which doesn't sound like the kind of environment that you're going to get around an active supermassive black hole, really.
No, so you've got to go a little bit further away from it.
Yeah.
So you've got to
just
move
back
out.
off.
Yeah, exactly. And in fact, the first piece of research was really looking at this and saying, well, you've got to be beyond what we call the snow line. And the snow line is a term that we use in, I think we've talked about before. Even
Yeah, I think so. A few episodes ago.
In our own solar system, we talk about the snow line because this is the dividing line, if you like, between the inner rocky planets and the outer gassy planets.
Okay, so why is it called the snow line? It's got something to do with freezing, I assume.
Yeah, so it's when water freezes, icy particle, volatiles, we say, freeze. And that makes them sticky.
Right.
So it means it's easier to build things because you've got this kind of sticky, icy stuff, which is also helping you stick together the particles of dust.
So is that the reason, I'm just piecing together my memory from that episode a few episodes back, is that the reason why you tend to get really big planets further out beyond the snow line and smaller rocky planets on the inside of the snow line?
Exactly.
Is that,
yeah.
Okay.
Yeah. So the sticky, icy, dusty stuff forms the cores of the gas giants very, very quickly.
Right. Okay.
And this is kind of the same process for a black hole planet. So the only difference is, I guess, in terms of scale. So in our solar system, the snow line is kind of between Mars and Jupiter. So 4 astronomical units, 4 times the distance from Earth to the Sun, something like that. Here we're talking about a few parsecs away from the supermassive black hole.
Okay, so we're about to get into testing Chris's memory of distant scales in the universe. Remind us what a parsec is.
So parsec is just over 3 light years.
Oh, what? So hang on, you're talking about a radius of a planetary orbit of light years away from the black hole?
Well, that's how far away you've got to be safe.
That's nuts. Like, okay, if you were to take from the Earth, how far away to the nearest star other than the Sun? How far away is it?
So we're just over a parsec, so we're about 3 and a bit light years.
So we're talking in the same order to the nearest star to us. That's the planetary distance from a supermassive black hole. That's okay. So when you said earlier, yeah, planets, but not as we know them. That's at least one of the reasons why. That's insane. Okay,
yeah.
Right. So you've really got to back off from an active galactic nucleus supermassive black hole in order to have a chance in hell of making
and these are what
planet.
we call low luminosity AGN. So these are the ones that are kind of
this is the easy one.
The calm ones. Yeah. They're not the big scary ones that we've talked about, firing off star formation in other galaxies and doing all sorts of wonderful stuff.
Good Lord. I love it. So yeah, okay, you can make a planet, but you've really got to back off a bit. Okay, fine. All right, we can absorb that.
Yeah. And then, okay, so you've got this new location where you can form planets. And the good thing is, the timescales work. So you can make them in about 1 million years, which is useful because, the universe is older than that.
Sure.
You've always got to check your sums when you're doing these kind of things.
Yeah, because that does come up from time to time. Occasionally it's like, but hang on, the amount of time required to do this thing that we observe in the universe is longer than the current age of the universe, we think. Maybe something's gone wrong there. Yeah, so that's good. It's always good to come within parameters.
Yeah. And so that was the first sort of piece of theory work that was done by this team. The second piece, which came out in July, was basically, let's refine this model. Let's figure out what sort of masses we might get. What are these planets really going to look like if they do form? We're going to use some better physics. We're going to use some more incorporation of the fact that you've got this wind, which we call it a wind. It's like the radiation coming from the AGN. So that's kind of pushing particles around a little bit.
Is that a bit like the solar wind coming from the sun?
It's the same concept.
Right.
Yeah. Radiation that comes from this AGN.
Only bigger.
Yeah, just a few orders of magnitude.
just a bit.
Yeah, so what they were able to do is they sort of looked at a black hole that was about 1 million solar masses, and that's it's a moderately small central supermassive black hole. Our one's a bit bigger than that. Our one's about 3 to 4 times that.
Right.
And they were able to say, okay, well, about 13 light years away from this black hole.
13 light years away. Okay, so we're up
Yep.
to several parsecs now.
Then you've got the kind of conditions where you've got this kind of sticky rocks. You've overcome problems of, the particles moving around too fast. And you can stick everything together and you can have some planets. And interestingly enough, the planets turn out to be quite big.
Okay. Like, how big? I mean, Jupiter's big, but how big are you talking about?
So between 20 and 3,000 times the mass of the Earth.
20 and 3,000. Now, how big is Jupiter by comparison in Earth masses?
So it's sort of, well, size-wise, it's about 100 times bigger than the Earth.
Right, so we're talking potentially up to 30 times the size of Jupiter.
Yeah.
That's quite big. Isn't that kind of pushing the limits of what can be a planet? I mean, I kind of thought Jupiter was already wandering in the direction of kind of a failed star, maybe, or is it not nearly that far yet?
I think we normally say about 13 times the mass of Jupiter is what we call a brown dwarf,
Right.
which is technically a type of star rather than a type of planet.
So the larger end of these planets is definitely into. But is that a planet though, or is that a blah at this point? Is that a star or a planet that we've just formed in our model?
Yeah. So, well, yeah. I mean, we have to say brown dwarfs are not like stars as you know them. They're not bright, twinkly, lovely things like the sun. They don't fuse hydrogen like the sun does. They fuse deuterium, which is much less efficient, so they don't really produce very much energy. They just kind of warm themselves up a little bit.
But they are fusing. They are fusing. The engines have been turned on. It is like, does that make it a star? Does that fact alone that it's got fusion reactions going on, does that make it a star? What is a star, Emily?
Well, that's a really good question.
Hang on, no, wait a minute. This is one of those moments where I'm looking at you on the Zoom and I'm thinking, surely, like, come on, astronomy, this is your bread and butter. This is what's a planet and what's a star. And I would have thought you'd have a really, really simple response to that. What's a star? And you're telling me that's complicated?
Well, there's no formal definition for what a star is.
What do you mean there's no formal definition? There's got to be. It's a star. That's what you do.
Well, yeah, maybe. I mean, I think that these brown dwarfs are pretty, they really don't. They do a little bit of fusion, but only just to heat themselves up a little bit, and then they sort of run out, and they just, they're only a few hundred degrees usually. They just sort of blob around. Are they just a warm planet, or are they?
Well, if they are a star, they're not a particularly useful one. Okay. Fair enough.
Yeah.
I'm amazed by that the notion that, well, stars, it's complicated. I think that's hilarious. Okay.
Well, they're a star when we want them to be, and they're a planet when we want them to be. How about that?
It's whatever's useful. It's a very pragmatic discipline that you're in here, Emily. So, okay, we're 13-ish light years away, and we've got planets, and I'm going to put big air quotes around that, which are potentially up to 30 times the size of Jupiter and may or may not be, actual bona fide brown dwarf stars at that point. These are not planets as we normally know them.
No, and it gets a little bit weirder again, because if you think something that's 13 times the mass of Jupiter, or a few times the mass of Jupiter, what you're probably doing in your mind is just scaling up Jupiter and saying, let's just make a bigger version of that.
That's what I have in mind. I've just got a really big Jupiter. Yeah.
But the problem is that Jupiter has a lot of atmosphere, like a lot of atmosphere, right?
It's atmosphere most of the way down, isn't it?
Yeah, it's a huge, huge envelope of atmosphere. These planets probably only have really, really tiny atmospheres, if any at all.
Right. So hang on, I'm trying to figure out what that looks like then. Because when I think of Jupiter, I think of like it's a gas giant, right? And so when I say, this may not be what your interpretation is, when I say its atmosphere all the way down, I'm thinking it's like you got to go a long way before you find anything that kind of looks like a solid surface. Yeah.
Yeah.
Or at least, a liquid surface or something, some kind of surface, something that I think of as a surface. So what are you talking about here then? When you say it's a very, very thin...
I guess it means that you've just basically got a very large lump of rock.
Really? That big?
That big. I mean, the core will be not solid. I mean, it doesn't take an enormous size of rock to have the pressure in the interior become so great that you've liquefied your solid material.
Okay, so from just the sheer mass, the sheer weight of all of that stuff sitting above it, you're going to put that core under enormous pressure and liquefy it. But as you get further out, there's a massive, enormous, it's just staggeringly enormous lump of rock. Really?
Yeah. So the thing is, there's just no gas for this rock to pick up in this distance from the black hole, because the gas has been pushed away from the radiation from the black hole. So that's much, much further out in the disk. So you just got no gas to make an atmosphere from.
So Jupiter, if we think of Jupiter, it's got this core which has been created because, working our way backwards, you've got the snow line, and so you've got lots of little sticky particles where the small bits and pieces have been able to sort of freeze and stick together and form clumps and bigger clumps. But you've also got then, once it gets big enough, it can start capturing the gases within the disk around the sun as these planets are forming, and it's capturing more and more and more gases, and you end up with this huge gas giant. Right? Is that vaguely right about Jupiter?
That's exactly right, yeah.
Okay.
But the thing that's different with our gas giants is that they had that gas there. Now, that gas wasn't there for very long, so they had to kind of grow, catch it, and then the sun kind of turned on, started its solar wind, and blew away the rest of the gas, and then they would stopped. That was it. There was no more atmosphere accretion. But
what you're saying about these huge planets is that, the clumpiness is there. You're way out of this ridiculous distance of the snow line, but the physics is still the same. And you're able to clump little bits together to make larger chunks. But that just keeps happening. You get bigger and bigger lump, but there's no gas for it to gather to become an even bigger gas giant. It's just got the lump on a massive scale.
Yeah. Because, the difference is that a black hole just doesn't sort of switch on one day like a star does, right?
Yeah, I guess that kind of makes sense. Wow. So enormous rocky planets?
Probably, yeah. Rocky icy. They're probably a little bit lower density than sort of the inner terrestrial planets. But, still pretty weird.
But hard surfaces. Like, in principle, you could land on it.
In principle, definitely.
In principle. I'm not saying this is going to happen anytime soon. I'm just saying in principle, in a way that you couldn't land on Jupiter and do anything useful. You could, in principle, land on... Like, I'm just trying to wrap my head around. When you say large, lump, rocky type planet, that's what you're talking about. You could sort of walk on it, in principle.
Yeah. And you might want to go for the lower end of that 20 to 3,000 times the mass of Earth. Would be my recommendation.
Well, I would have thought if we're going to try to do this at all, there are probably a whole bunch of things that we need to think about before we, start strapping people onto a rocket and sending them in the direction of one of these things. The first of which being finding one?
Well, I've got a quote from the first paper here from November from Wader. The standard techniques of, and I'm sentence in context, and they were talking about the standard techniques of finding exoplanets. The standard techniques are hopeless.
Well, let's not beat around the bush here. Why don't you tell us what you really think, guys? What do they mean by that?
I enjoyed that statement.
What do they mean by that? Like why? Why is it hopeless?
It means that all the ways that we currently use to find exoplanets around stars, which are, for the most part, quite close to us in our galaxy. Mm-hmm. We've talked about things like transits. We've talked about using Doppler shifts, all these kind of techniques, even imaging directly. All of these things just don't work when you're right next to a black hole, because this whole environment is so shrouded in, it's so opaque because of this sort of dusty torus. You just can't even see into it.
So all of the ways that we would normally do this, let's go. We think that there are going to be planets. Let's go and look for some. Our normal techniques are not going to work. So, any suggestions? Any thoughts here?
Yeah, they made a couple of them, but they were very kind of like, You could maybe because you can sort of see, you can make measurements of the kind of the dusty disk broadly, spectroscopically. So maybe you could kind of look for some opacity changes in that disk that were related to kind of as the disk was trying to coagulate, that might change the opacity a little bit, but it was kind of pretty speculative. And only warranted a sentence or so.
Yes. With a lot of asterisks in it. Yeah, maybe you could do this, but look, we don't know. Who knows? Hey, Emily, how big is the accretion disk around a supermassive black hole like we're talking about? I mean, if we're going out to several parsecs, in which we're talking about, this is where you might conceivably, possibly, if you found a way to look for it, you might find a planet. But presumably an accretion disk would go much, much bigger than that. So how big is the area of influence around a supermassive black hole? I mean, arguably it's the whole galaxy in a sense, because the whole thing's swirling around, etc. But the accretion disk, how big is that?
Well, I just pulled up from the paper that there's a little cartoon from paper 1, which shows kind of a cross-sectional cutaway of what, supermassive black hole in the area, big disk. So where we're talking about is kind of like around 10 parsecs away. So, 30 light years or so up to that for our planets.
Right. So that's about 3 times the distance that you'd been talking about out to the snow line. Is that right?
Yeah. So that's kind of where we're talking about these planets forming. And then they've got kind of a thin disk all the way out in this diagram up to about 100 parsecs.
Wow. I mean, what it really points out to me is, like, we get used to certain distance scales when we talk about this stuff, and the solar system, now that it's becoming pretty familiar to us as a species, it wasn't that long ago that even the solar system was completely mysterious, but now we're fairly comfortable with the notion of a star and a bunch of planets going out to, the outer ones, Neptune and even Pluto. Will include Pluto. And then that's a sort of a distance scale of solar system kind of size. You're now introducing a distance scale which is scaled up by a massive degree in all ways. You're talking about the central, star-like object, whether that's an actual star or a supermassive black hole. And in the case of our sun, or in the case of the supermassive black hole, which is several million suns worth of mass, that's a massive, massive spectrum of what you can have in the middle of this system. And then out to sort of, Earth distance scales, astronomical units, 1 AU, all the way out to several, if not dozens of light years of distance, the distance to the next star and beyond, being conceivably something that we would talk about in the same breath as a planetary system. Like, that's nuts. How do you astronomers cope with that kind of ambiguity about what we talk about when we say, oh yeah, that's a planetary system? That's fine.
Yeah, we're very good at writing down big numbers. We've just got to kind of keep ourselves a little bit grounded, and that's why we do have all these crazy astronomical units that things like parsecs, because it becomes much, much easier to talk about parsecs than sort of millions and millions and millions and millions of kilometers, right?
Yeah, and it kind of scales it all down to, well, we're just talking single numbers now. We're just talking, numbers in the units or the tens rather than ludicrous numbers of zeros. But do you ever get caught out by it? Like, do you ever feel the need to go and breathe heavily into a paper bag for a bit to just calm yourself down when you think about some of this stuff?
Yeah, I guess so. But this is what I love about astronomy. This is one of the things that drew me into it, is the mind-bogglingness of the unimaginability of some of these things that we talk about. That was always something that I really enjoyed. Maybe I'm just very narcissistic and I just want to break my brain all the time.
Yeah, we've gotten used to that concept. Let's go and find one bigger. I'm sure we can do that.
So if you're sort of struggling with the distances that we've got, planets going around black holes at distances you might think of normally stars going around them.
Which, can I just point out, I am struggling with that. Emily seems to be fine with it, but I'm just in a corner here, rocking backwards and forwards mentally at the moment. But yeah, carry on.
Well, here's the amazing thing. We can flip it all around and say, well, let's talk about stars orbiting a supermassive black hole at the distance you'd normally talk about planets.
Wait, sorry, what? Stars? Okay, we've talked about this in a previous episode as well, I think. I think we've come across... Well, actually, Nobel
Episode
Prizes,
16.
wasn't it? well, back to 16, but
we
also
talked
more
about black
recently.
holes and Nobel Prizes.
Yeah. So this had come up. We've talked about this on a couple of occasions, but hang on, back up a minute. Stars orbiting like planets. Okay, talk to me about this. Bring me in.
So these are our squeezars.
This is our second new word of the day.
Well, yeah, it's amazing because I must hold up my. So Blanets is a 2020 word. That's fine. I'm
Okay.
good. You know, we can talk about new word 2020. Maybe it should be the new word instead of lockdown for the OED or something.
I would fully support that. I think we need to write to our local MP.
But squeezars, I was completely unaware, is actually a pretty old word. It's from
Really?
2003.
Wow.
Yeah,
Which
but I was just completely
makes me
oblivious
feel
to
really
it.
old to think 2000. That's not that old. No, it actually is. It's 17 years ago, Chris. Oh, yeah. Okay. Right.
Yeah, I know. Time is awful. So squeezars are stars that go so close to a supermassive black hole that they orbit faster than about 3% of the speed of light.
Now, 3% isn't a very large number, but when you're talking about the speed of light, 3% of the speed of light is ludicrously fast. Like, that's really, 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 really quick. Now,
That's 9,000 kilometers per second if you want to kind of speedo reading.
okay, but we know, thanks to Albert Einstein and all the thought that comes around him and after him, we know that these things are all relative, right? Because, right now, here on the face of the Earth, we are going around the sun at some ridiculous speed, and we don't even notice. It doesn't even, ruffle our hair, as Tim Minchin once said. So, speed is relative, and these numbers can be very big. I'm right, aren't I? That the sun is at this very moment, our solar system at this very moment, is itself orbiting around the center of our galaxy, isn't it?
Absolutely.
Do you know
Yep.
off the top of your head how fast we are traveling around the center of our galaxy?
We travel about 220 kilometers per second.
Okay, so that's fast, right? That's quick. We are moving at quite a pace around the center of our galaxy, and that's kind of relative to the galaxy itself, and we don't really notice that. But how fast did you say this star is going around the supermassive black hole?
To be called a squeezer, you need to be going more than 9,000 kilometers per second.
9,000. So we're going a couple of hundred, and that's 9,000. So that's like tens of times faster than we are currently moving, which is very, very fast indeed. All right, so we're zooming in right on the center of the galaxy here, aren't we?
And we've been here before.
We have been here
Well,
before.
maybe not us literally, but
Yes.
we have talked about this area of our universe before.
We have. So take us through it again.
Yeah, the Milky Way galaxy. So we've got a supermassive black hole at the center of our galaxy. It's about between 3 and 4 million times the mass of the sun. But what you're going to have to keep in your mind here is that it is small in terms of actual physical size, right? Black
Yeah.
holes, big mass, small area.
Yeah.
I didn't write down today how big it is, but it's not very big.
I seem to remember it's sort of
I think it's
roughly, isn't it solar system sized or something like that? It's in the order of
Well,
that?
it's smaller than that, but yeah, it's maybe like a couple of times the size of the sun or something
All
on
right,
that
okay.
order.
Okay. Anyway, small, but ludicrously massive. Yep.
And we've talked about how we've done measurements of stars orbiting this, because it's just an inky black spot in the middle of our galaxy. There's nothing physically to see there that we can detect. We can detect X-rays coming from this broad area of our galaxy, and we can see stars which are orbiting something, and these stars are orbiting in these crazy, crazy orbits because of the gravitational force is so incredibly strong.
Yeah. And again, it's just orbiting the way the Earth orbits the sun, but it's orbiting something very, 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 very massive. And these stars are moving very, very, very fast for stars.
Yeah, so we talked about S2 all the way back in episode 16.
Yeah. So tell us about S2 again.
Yeah, so S2 had used to be the fastest star, it's the fastest squeezer in our galaxy. And when we did the episode, which was all the way back in 2018,
Goodness, all those years ago.
it was actually going to closest approach, and that was important because it's on a 16-year orbit, and we want to observe kind of the whole orbit to test theories of like general relativity. How does gravity work at these very, very insane high masses?
Yeah, because for most orbits, you can just use Newton, can't you? Newton's physics, the old physics, the classical physics, works really, really well for most orbits. But even within our own solar system, Newton starts to get a bit hazy around the edges when you get in close to the sun, like Mercury, right? There's Einsteinian, there's general relativity stuff going on with Mercury, isn't there?
Yeah, yeah. You need to include general relativity into your equations to calculate Mercury's orbit correctly.
Yeah, for Mercury you need general relativity, and that's just with the sun. That's just with a common or garden variety yellow star. When you get in close to a supermassive black hole, it's all about the general relativity. And so when S2 gets in nice and close, presumably by measuring its orbit, you can get some really good comparisons between is general relativity applicable here or not, to quite a good amount of precision.
Yeah, exactly. So S2, when we did the episode, was the fastest orbiting star around our black hole. It was actually superseded in 2019 by S62.
S62. Are these S's, S2, S62? They're presumably anything from S1 all the way out beyond S62. Are they stars that are orbiting this supermassive black hole? Does the S stand for supermassive, or does it stand for Sagittarius because we're in Sagittarius?
That's a good
part
question.
of the sky?
I was thinking it stood for Squeezar, but maybe it's Sagittarius.
Maybe it just stands for star, and they're numbering them as you go out.
Yeah. Well, yeah. They're numbering them, I think, as they're found.
Right. That makes more sense than my idea. Yeah. That's why you're an astronomer and I'm
not. So that in 2019, S62 was discovered to be the fastest. It had a 9.9 year orbit and is orbiting at about 118 astronomical units.
So. Wow. So that is, for a star, that's really close.
Yeah, it's kind of twice Pluto.
Wow, and they're going several % of the speed of light at that point.
Exactly. Now, an interesting thing is that this is why this sort of came across our radar pretty recently, is that there was a new paper published in August this year, so not too long after Blanets.
Yeah, we're not so far out of date at this point. We're catching up. July, August.
We're getting there. From Psycho et al. And what they were looking at is they were looking at two newly discovered Squeezars, which were S4714 and S4711.
Okay, catchy names.
And they have now found not only the average closest star to the central supermassive black hole, which is 4711, but the speediest, the new speediest Squeezar.
Oh, right, so we got a new record breaker.
Yeah, which is S4714.
And so how close and how speedy?
Well,
we need numbers.
Yeah, let's start with 4711. The closest. No, this is the closest on average.
So it's not closest approach, but it's closest generally. So S2 gets very close. And what was the other one? S62?
4714. Yeah, and 62. Yeah.
62. They are presumably on very elliptical orbits. So they get in really close and then they go quite a long way away. And they come in really close and get a very long way away. Whereas this new, on average, closest one, is it more of a closer to a circle type orbit? Is that?
Yeah, exactly. Yeah, it's not quite circular, but it's less elliptical than the others. So this one's on a 7.6 year orbit.
Wow. Okay, that's getting really quick.
Yep, 144 AU. So again, this is just nearly 3 times Pluto's orbital distance. But that's the average distance, right? Mm-hmm. So even though I said S2 was coming into 118, that's its, as you say, closest approach rather than its average distance. Average distance is further than that. So it has the shortest orbital period, this 4711, and the smallest mean distance, 2 records.
Goodness me. Well done. Well done that star. Well done that Squeezar. So that's exciting. And the other one was
S4714, which is the new record for the speediest, and I think it's got the closest approach. Therefore, I didn't write down what the closest. Yes, I did write down the closest approach. Yeah.
Okay, so it's got 2 new records as well. Do they? I guess they would come hand in hand, wouldn't they? That
yes.
In order to be the speediest, you have to be getting the closest. That's how that works. Yeah. Okay.
So S4714 is on a 12-year orbit, but when it is at closest approach, it is only 12.6 astronomical units from the black hole.
Wow. So where does that put it in solar system terms?
So Saturn is at 9 astronomical units, and Uranus is kind of 18.
It's just a bit beyond Saturn. Wow. That's absolutely nuts. And how fast is it going at that point?
So it's going 8% of the speed of light.
8%, rounded up to the nearest really good number. And that's a tenth. It's like, holy cow.
24,000 kilometers per second.
Per second. That is nuts. Okay, so now might be a good time to ask the question, why is a squeezar called a squeezar? What's the squeeziness? Why a squeezar?
What's interesting about most of these squeezars, because they're on these elliptical orbits, they get incredibly different tidal forces as they move towards the black hole and then when they move away from it. So the change in gravitational force that these stars experience kind of is huge. So just that change in force causes them to kind of morph, and well, we haven't seen them morph, but you know, the difference in tides, like the difference in tides on the surface of the Earth, causes the oceans to rise up and fall down.
Right.
Same thing happens with plasma and stars. So they're probably being sort of squeezed and tugged and gravitationally thrown all about.
Particularly when you're coming in somewhere around the orbit of Saturn, moving it, let's call it 10% of the speed of light, there'd be a bit of squeezing going on. That's just bloody amazing. So you're talking about S, and then the number is in the 4,000s. I remember seeing some data and some animation from Andrea Gez's group, who've done, like, she and colleagues got the Nobel Prize this year for their, was it this year? For their work on, what even is time? For their work on these stars around the supermassive black hole. And I remember seeing some animations of maybe, a dozen or so stars. Like, how many stars are being studied around this supermassive black hole? Like, does that number sort of stand up to, we're looking at thousands of these things now, or is that just coincidence?
I think we've only got a handful still. I don't know why the numbers have gone so high. I think it might just be from initial catalogue identifications of candidates, and then kind of most of them turn out to not be super great. So I think we've got maybe on the order of about 10 good candidates that we can track. Right. Yeah, maybe it's a few more than that, but they're not super common, I think, these things.
This is like this particular podcast is blowing my mind somewhat on a number of different levels. We've had planets which are just stupidly big lumps of rock, ludicrous distances away from very, very heavy supermassive black holes, and then we've got stars where planets should be traveling 10% of the speed of light in crazy ways. Emily, how the hell do you measure this stuff? How are these people doing this?
Yeah, so we do have similar problems with the center of our Milky Way galaxy as we do with other black holes, supermassive black holes and other galaxies, and that it's very difficult to see very close to these centers of these objects. What we can do with our galaxy is use infrared to sort of peer through all the gas and dust that's shrouding the center, and get some signatures from these stars. Right,
because a lot of types of light, like visible light, is all blocked. You can't see with the naked eye the center of the galaxy. You'd expect to be able to look up and just see this really, really bright part of the Milky Way, big bright part of the sky. But you can't, because there's lots of dust and stuff, and so it's actually kind of dark. But the infrared gets through. It's not blocked by all the dust and stuff.
Yeah, exactly. Okay. But you do still need a big telescope. So we're talking about observations made on the VLT, the Very Large Telescope in Chile, which we have given a few good shout-outs to.
We have. We love the VLT, if only for its wonderful name.
Now, here's a little rabbit hole, which I did go down, which I think you might like.
Go on, then.
So the paper mentioned the instruments that they were using, which were called NACO and Sifoni.
NACO and Sifoni. Okay. Are these astronomical acronyms that we're going to go with here?
Oh, yeah.
Okay. NACO and Simone, was it?
Sifoni.
All right. Go on, then.
Okay, so I'll go with the first one, the second one. I thought, well, I better check what these acronyms mean so that I'm well educated. Sifoni, Sifoni, is the spectrograph for integral field observing in near IR.
Very nice. Okay.
Okay, I can kind of live with that.
Sure. And I mean, disappointingly, they haven't tried to turn that around and turn it into, a recognizable word, unless it is a recognizable word in another language, and I don't know that. But you do see scientific acronyms working really hard, like just doing a lot of legwork in order to, like, if we just swap a few of these words
Too
around,
hard sometimes.
then we will have a recognizable word. We can call it giraffe or whatever it might be. It's like, or you could not, it's a choice. And they haven't in this case. They've just coined a new word. Okay, fine,
okay,
good.
so that's fairly bog standard astronomy acronym, right?
Good.
Then there was NACO.
NACO.
And this is where I got slightly amused, and I'm glad you were 5 minutes late, because I was able to spend about 5 minutes Googling this to figure out what NACO was. So NACO is an acronym, which is an acronym.
It's an acronym within an acronym. It's acronym inception.
NACO is an acronym of NAOS and Kanika.
Yeah, and they are?
NAOS is the Naismith Adaptive Optics System.
And the other one?
Well, Kanika, it took me a while to find this one, but it is the Coude near-infrared camera.
You can't do it. Look, sorry, I'm going to put my foot down on this one, all right? I have issues with astronomical naming. We know this, right? People who've been listening to the podcast for a while know that I get upset by these things. But I'm going to say, categorically, it's not all right to make acronyms out of acronyms. You're just going too far at that point. Just make up something new. Just give it a name. Just call it, I don't know, Barry or something. Just give it a name. Stop with we don't want now a multi-level acronym that you've then got to go and Google for 15 minutes in order to figure out what even is this thing. That's ridiculous. Emily, I want you to do something about it.
You might be encouraged, therefore, that NACO has now been decommissioned and replaced, I think, by Symphony. But that did tickle me a little.
It's been decommissioned, if only because that was just ridiculous. Stop it. That's it. We're taking away your funding. We're giving it to these guys who've got a much more sensible acronym. They haven't even tried to turn it into a real word. They've just put the letters down and pronounced them. End of story. There we are. All right. Sorry about that, everyone. I haven't had a good rant in a while, and it feels good to let that out at this point in 2020. So thank you for humoring me on that one. Emily, Blanets, Squeezars, mind-blowing stuff. But at the end of the day, where does it get us, right? The time-honoured way of ending our podcast is with a bit of a so what. So I'm going to throw it at you. So what? What does this give us?
Well, it turns out black holes are pretty mysterious objects, right? We don't know as much as we'd like to about them. They're tricky to observe. They're tricky to take photographs of, certainly.
Although if you'd said that 10 years ago, it's not tricky. It's impossible. You can't do it. And here we are.
Yeah, well, there you go. But they do contain some of the most extreme environments for testing physics that we have, and that's not just gravitation, like we talked about with the Squeezars, extreme gravitation. It's extreme ionization. It's extreme radiation coming from these AGN, these jets. They're just extreme things. They're extreme with a capital X. I think.
Hard to get more extreme, really. Yeah. I mean, there's probably ways, but this is always going to be up there as your baseline. Are you more extreme than a supermassive black hole? No, well, there's the door. Off you go. Not interested.
So, yeah, but I mean, there are practical things. So, for example, the Squeezars, we're looking at things like we can constrain the rotation of a black hole, which is really important. If you don't understand how a black hole rotates, you actually don't understand its mass, which is interesting and very difficult physics that Professor Roy Kerr, for example, looked at.
Yeah, that's right. We were talking about that when we talked about the Nobel Prize this year. Is the very simplest mathematical solution you can do that is black hole-like is just a black hole. It's not rotating. It doesn't have any charge. It's just nothing. And then when you go up from there, say, well, let's try a black hole that is rotating. Whoa, now hang on a second. That's really, really hard. And so tying all of these things together and being able to nail down. So how is this black hole rotating? It's actually really important.
Yeah, exactly. And then on the sort of the Blanets side, you're sort of looking at these environments and doing them sums and actually, okay, you're hypothesizing whether or not these planets that we may or may not be able to see exist. But it's all about dust and physics and looking at the interaction between the black hole and its local environment, which ultimately will tell you about the black hole itself, because that's the stuff it's going to consume. That's where its energy source is. So it's all interesting stuff that we can learn more about black holes.
Well, another episode of the podcast that blows my tiny little mind. Emily, you do this to me every single time, and it doesn't get any more pleasant for me to have my mind just torn apart like this, but you seem to enjoy it.
I love it. Do it every day.
Do you ever worry that, I guess it's the opposite. I asked earlier whether or not this kind of stuff, sends you off hyperventilating into a bag. Do you ever worry that it'll go the other way, that you just get so blasé about talking about the most extreme stuff that you could possibly imagine, and it's like, it's just a supermassive black hole?
I think that would be a danger if I wasn't doing things like syzygy, because syzygy is one of those great things that makes me sort of say, well, actually, what does that number mean? Let's put that in a human thing. Let's not just put 42 zeros after the size of the universe. Let's think about what that is for a human.
And you get to describe it to me and then watch me pick my jaw up off the floor and say, oh yeah, maybe that is surprising. Yeah. Well, I'm glad I can help you out there. I'm glad I could offer that service. Listen, if you're listening at home and you similarly, like me, I put too many lilies in there. You similarly, like me, have been picking your jaw up off the floor, and you want to write in to explain to Emily just how amazing this stuff really is, or you just want to get in touch and say hi, drop us a line, ask us a question. You never know, we might do an entire show about your question. Then there are a number of different ways that you can do that. Emily, name at least one way that people can get in touch with us.
At least one?
At least one.
Well, let's go with good old Twitter first.
Let's
Twitter is fun. Twitter is great. Yes, so we are at SyzygyPod. That's at with an at symbol, and then Syzygy, which is SYZYGY, and then pod, which is pod.
Yeah, all one word, at SyzygyPod. We are there. Do we have that handle anywhere else, Emily?
Oh, it's like we planned this in advance, Chris.
It's like we did. Yeah, it's like we had a plan.
We're SyzygyPod on Facebook. We're on Instagram. We're on other things.
Have you been TikToking lately? I haven't been TikToking.
No,
I can't keep up with the kids and their TikToks. But we also have a website, which is syzygy.fm, where you can go and find all of the past episodes, all of the show notes and all of that stuff, as well as our great wall of thanks for all of our wonderful supporters over on patreon.com/syzygypod. That's another one. If you want to help out the show financially, then you can wander over there and pledge a couple of bucks, a couple of quid a month to help us keep the lights on, keep the electrons flowing through the website, and help us to do, when the world does eventually completely open back up again, things like live shows and festivals and all of those fabulous things that we really enjoy doing, to actually see some members of the listening audience, which is always great fun. The other way that you can support the show, the best way you can support the show, is by telling people. Tell your friends and family, and say, there's this show, and it's full of amazing stuff like, have you ever heard of a Blanet or a Squeezar? No, then go and listen to Syzygy. That's what you got to do. Tell them about it. Spread the word. Leave us a review on your podcast client of choice, whether it's Apple Podcasts or whether it's Spotify or wherever it might be. Leave us a review. Tell people how much you enjoy it. Give us a few stars. Help us to rise up through the noise so that more and more people can share in the jaw-dropping delight of learning about the universe. But I guess that's where we're going to have to leave it. Emily, the next time I speak to you, you're going to be on the other side of the planet.
Well, hopefully, or maybe
hope.
we can. Well, we might even be able to squeeze another recording in before I go.
Right, I see what you did there. Very nice. Well, look, if we do manage to speak before you go, then that'll be coming up real soon. And if not, then I'll be speaking to you sometime towards Christmas from your hotel of isolation down there in New Zealand, which will be entertaining in and of itself. So until then, take care, everyone, wherever you are. Emily, take care. I'll catch up with you again soon.
See you later.
Bye, everybody.
I don't think I'd want to spend 2020 on a Blanet. Was just my final thought.
Could it be worse?
I think it would be worse, because even if it's kind of this like fully irradiated lump of rock that's very, very high gravitational field because it's very massive, the problem is that 2020 might last something like 1 million years on a planet.
Oh, no. No. Okay. No, you've just won me over. Yeah, it could be worse. It could be worse. You could be on a planet and it could be lasting like forever. Yeah. Let's not do that.